Hello and welcome to the final project. My name is Taya and I'm in a group with Ariana, Nav, and Sarah. We decided to evaluate mile times of students at River Valley. In order to do this, we looked at the mile times from a random PE class on campus. We used the same class for both our pairwise data and the data used for the t-scores and 1 proportion z interval. For the pairwise data, we took the difference between the times of the same student at 2 different times in the same term. We used the set of times from the first mile they ran for our non-paired data to use for our t-scores in 1 proportion z interval.
Hi, I'm Navdeepal, and I will be discussing if all the conditions are met. I will first discuss conditions for pairwise data. The first condition is the paired data condition. This is met because each value is the mile time ran by the same person. The independence assumption is met because there's no reason to believe that the difference in speeds of one pair of mile times could affect the difference in speeds for another pair. The randomization condition is also met because we chose a random PE class and they ran in random assigned lanes. The 10% condition is met because 24 kids are less than 10% of all RVPE students. The nearly normal condition is met because the histogram of the time differences is unimodal and almost symmetric. Second, I will discuss the additional conditions for a 1 proportion z interval. As previously stated, the 10% and randomization condition are met. The independence assumption is met because someone's mile time would not affect the mile time of another person. At first, the success-failure condition was not met. However, we bypassed this issue using the +4 model. This allowed us to use a small sample, making their mile time under 11 minutes counts as a success, and over 11 minutes is a failure. We tried to do a 1 proportion z-test, however, after searching online, we were unable to find the true proportion. All the conditions for a t-test and t-interval are met. As I've said before, the independence assumption, the randomization condition, 10% condition, and the nearly normal condition have all been satisfied. As you can see, because all the assumptions and conditions are met, we can proceed using this data.
The data that we collected was the mile times of a randomly chosen high school PE class. We received 2 different times for each student in the study, so that we could have pairwise data. Since we had 2 different mile times, we wanted to compare their differences. We subtracted the first mile time from their second mile time, so that we could analyze the change. The first set of mile times we called the pre. I ran a 1-variable stats test on it in order to find out some basic information. The mean of the pre-mile times was 698.75 seconds. The standard deviation was about 112 seconds. The number of times sampled was 24. The quickest time was 477 seconds. The middle time or median was 702 seconds, and the slowest time was 937 seconds. I ran the same calculation test on the post data. The average mile time was 595.7 seconds. The standard deviation was about 117 seconds. The fastest time was 428 seconds. The median time was 596 seconds, and the slowest time was 1,035 seconds. The number of times sampled was 24. Since the data is paired, it had to be the same as the sample size for the pre. The average of the change was about negative 103 seconds, which means that the second mile times were usually quicker than the first. The standard deviation was about 163.55 seconds. The biggest improvement was negative 386 seconds. The median change was negative 108.5 seconds, and the biggest increase was 307 seconds. Looking at the change data, we can see that 18 out of the 24 students improved their mile time on their second run. Part of our assignment was to find the p-value of the data that we collected on a class's mile times. The p-value would tell us if we should reject the null hypothesis or not. Our null for the individual pre- and post data was that their average times would be 11 minutes or 660 seconds, which would be H sub O is mu equals 660 seconds. Our alternate hypothesis was that the average times would be below 660 seconds, which would be written h sub a is mu less than 660 seconds. The 660 seconds was what we set our cutoff for success or failure, since under 11 minutes is the requirement time for passing the mile in PE. To find the p-value, we would have to perform a t or z test. In our case, we thought we should do a t-test because we didn't know the standard deviation of the entire population that the mile times applied to. Unfortunately, after searching the internet, we were not able to find the standard deviation of average high school mile times. We figured that was okay, and we could still continue with our t-test. Once again, we hit a wall. It turns out that we didn't have all of the necessary information for a t-test either. Apparently, we need the given mu of all the mile times, which we couldn't find on the internet either. Before we knew that we needed this critical piece of data given to us, I tried to perform the t-test several ways. Since we didn't have the given mu, I used the average that I found from the one variable stats, which was 698.75 seconds for the first mile times that were located in list 1. I also selected the mu does not equal 698.75. The t-test gave a t of 0 and a p that equaled 1. However, this didn't seem right, so I ran it again, but this time as the average equaling 0. Once again, I selected list 1 and selected u doesn't equal 0. This gave a t-value of about 29.9 and a p-value of about 6.5 e to the negative 20. This seemed a little more reasonable, and we assumed that the extremely small p-value showed that we should reject the null hypothesis that mile times stay the same. After we tried doing the t-test with 660 seconds as the given mu, since we found out we had to have a separate number as mu. Once again, I used list 1, and mu does not equal 660. This produced a t-score of about 1.66 and a p-value of about 0.11. We also tried the t-test with mu less than 660 seconds, which changed the p-value to about 0.94. Then we tried the t-test with mu greater than 660 seconds, which changed the p-value to about 0.06. Looking at the data and the results of the t-test, they didn't match up. The high p-value of 0.94 meant that the probability of a mile time being below 660 seconds was high, and a lot higher than the probability of being above 660.
For the interval proportion of our project, we were forced to do a 1 proportion z interval because we lacked the true mean for our data. Before we could perform the interval calculations, we had to meet all of the conditions required. We met all of the conditions except for the success-failure condition, which we bypassed by using the +4 model to get our p-squiggle. After plugging all of the essential things into the calculator, we found out that we are 95% confident that between 10.9% and 47.4% of the students will succeed in passing their 11-minute mile.
When we first began our project, we had difficulty deciding what type of data we should use. We first wanted to use the data from Nav and Taya's last project, but realized it was not useful with this project. The paired data condition was not met because it was a very simple survey and not a collection. On multiple occasions, we asked Mr. Jenkins for help on how to best gather data. He offered us the idea that it was best to use a study that had already gathered information before. We then randomly selected a River Valley PE class to compare students' mile times. We converted our times from minutes to seconds, then evaluated and analyzed our data. We brainstormed together at Starbucks and wrote our script. We came up with our conclusions, which is we reject the null hypothesis. We also did a two-tailed test. Then in class we talked to Mr. Jenkins about our t-test and z-test and discovered that we failed to add non-pairwise data. Taya and Sarah then had to both recalculate their portions of the work for our project to flow correctly. Jenkins then explained that we need to use a one proportion z-test if we could find our true proportion in a regular t-test. He told us to use means for our data set as a standard for success-failure rates. We learned that if success-failure doesn't match the +4 model can be used. We had difficulty finding the true proportion for our z-test and were unable to perform this test due to the inability to find the true mean. We learned from Mr. Jenkins that we can do tests without the true proportions except intervals. That we could do all the tests, or we can't do tests without the true proportion except for the intervals test. Sarah went through an exhaustive search, and in the end, her entire section ended up being entirely hypothetical.
Contrary to what it may seem in this video, all of us in the video put forth the same amount of effort in the video, although it may seem like one portion was a lot longer than the rest of the portions in this video.